All right, I think we got enough people, so I'm going to go ahead and get started. CNC Winder is one of RPL's most important machines in our lab. And it does one thing, and it does it well. It makes carbon fiber motor cases from carbon tow. These motor cases basically form the basis of all of our solid rockets, and these have been used on things like Fathom 2, Traveler 4, Earthshaker, and they will be used on pretty much all of our solid rockets going forward. We're always kind of iterating on the design, but we have a pretty consistent basic design going on the that we haven't changed much in the last 5 years or so. So this is going to be a bit of a thick presentation. I've got a lot to cover. The first half of it is going to focus on winding theory. So like, what kind of shape are we trying to wind in a case? How does the toe behave? What's the actual like calculations for winding one TABA of a case? And I'll explain what a TABA is in a minute. Then we're going to talk about the winder mechanism. So like specifically how it works mechanically and electronically, and kind of what's wrong with it and what I think might need to be done going forward to improve it. So basically the goal of this part is to explain what shape we're trying to make with what shape we're trying to wind and how we actually make the winder create that shape. So fundamentally, winding is about constructing a carbon fiber motor case from tow. So when the winding is running, this is what it looks like from the side, and this is what it looks like from the bottom. So we've got, so basically there's a cylinder called the mandrel, and then tow is being wound onto that cylinder. This is kind of what tow looks like when it's realistically drawn. And I did my best with the drawings in this. I'm not an artist, so I did my best. I'm sorry if they're I can't draw a straight line to save my life. But anyway, and then tow is, of course, the material that's actually being wound on here. So what that is it's formed from, it is formed from a bunch of carbon fiber threads that are put together, individual fibers that are put together into kind of a flat tape-like substance. So tow is what we actually make our cases out of. Let's see, and all right. So basically, when the winder works, these tow strands are woven in sort of a diagonal pattern. Now, this doesn't look like this on the case over here because some of the strands are hidden. But if you had X-ray vision, this is kind of what it would look like. Each strand kind of runs directly next to the other strands. You can kind of see the seams here where it's woven back and forth. Make sense?
Yeah.
All right. Good to hear. So one thing to know about carbon cases, I'm not going to go in, I'm not a mechie, so I don't know too much about the actual design procedure for the cases, but I will say that one of the interesting things about carbon fiber design is that you can, by varying the angle that cases are wound at, you can actually control what type of strength they have. Like a case wound with a very tight angle, which we refer to like a dense layer, nearly 90-degree wind angle, is one where it's kind of like it's in a tight roll. And those cases have a lot of hoop strength, like they can resist a lot of pressure pushing outward. However, they don't have much axial strength. They can't resist as much pressure pulling from the ends. Whereas a case that is wound at kind of a more balanced angle, I believe 59.5 is the angle that gives the best performance, have more axial strength, so they can more resist pulling. I think 59.5 is the angle where the hoop strength and axial strength are equal. So it's historically what we used to use just because it was kind of straightforward. And of course, we need both axial and hoop strength as there's a lot of pressure from the rocket motor inside the case that's pushing both outward in hoop strength and outward in axial strength. Make sense? All right. So basically each wound layer that the winder produces is composed of TABAs. That's an RPL term. I don't know if anybody else in the world uses it, but we refer to it as a there and back again pass. So each TABA represents one pass across the mandrel and then back to where it started. So each layer of the case is composed of a bunch of TABAs, and then a whole number of TABAs are needed to complete one whole layer of the case. Let's see. Oh yeah, before we keep going, if you guys want to follow, we're going to be doing a demo in a little bit. If you guys want to follow along with the demo, you're going to need to download a thing, which I'm sure a lot of you have already seen. I'll post the link in Zoom chat for people from not RPL. So go ahead and get this ready to run. Let's see. All right. So each TABA in turn has a couple of different steps. So the very first TABA of the entire layer of the case is has an initial lock step. So then that is going to basically be winding in place around the mandrel. Then we have a there pass, which is going in one direction along the mandrel, so to the left. Then finally we have next we have a far lock, which is basically something that anchors the toe at the end of the case. Keeps it, because if it just immediately went backwards, it would kind of start slipping. But the toe is sticky, it sticks to the case, so this sort of far lock is enough to hold it in place. Then we do a backwards pass, which, as you might imagine, just means going back to the start point of the case. And then finally, we do the near lock, which is the lock at the 0 point, which holds it in place at that end. But why are all of these locks, right? Why not just wind the case? So the lock steps are really important to anchor the toe at the end of the case. However, they do have some downsides, which is they cause what's known as end effects, which is basically a big, like, kind of horn-shaped pileup of toe at the end of the case. The closer it gets to the end, the more you get a huge pile. And the more layers you wind on top of each other, the bigger this pile gets. Sometimes we have to actually, like, cut it off between wound layers. I think that's what we started doing on Traveler to just so that it would be more manageable for the winder. It also creates what's known as an interface region. So the interface region basically just is where the toe angle gradually goes from the normal angle up to like infinity, or going completely straight up. Wait, no, that's just 0, not infinity. What am I saying? Gradually goes to pointing straight up. So that there's kind of an interface region where the winding parts of the case get closer and closer together, and the case gets a little bit thicker until finally you hit the end. So both of these regions are kind of undesirable effects. The interface region is a lot thicker and bulkier, and the end effects are just huge and have to be removed. So, but they're kind of a necessary evil, because without them, we wouldn't be able to wind the case at all. Okay, so I bet all you guys are really struggling to visualize this right now. I definitely would understand if you were. So I'm going to go ahead and use something that is going to help visualize, which is the winder simulation that I shared. So this is something we've been working on over the last couple weeks that is going to help actually explain what is going on when we use the winder. Let's hope that this is actually going to work properly on my machine. All right, cool. Looks good so far. There we go. That's showing up for you guys. All right, so what this simulator is it's something that's able to model the actual physical behavior of the winder. So as you can see, if I move the, I can move the carriage with the mouse, and you can too on your machine, then that will actually move where the toe is currently being deposited. This is what it would look like if you were actually in lab using the winder.
Jamie, the screen went green.
Jamie, it's green.
Ah, dang it. My Zoom does this sometimes. All right, is that better?
Yeah, that's good. Oh, it's green again.
Dang it, really?
Nope, it got bad again.
I wonder maybe if I don't use video mode. That any better?
Yeah, that's good.
All right, probably not the best FPS, but at least you can see what's going on. So this kind of demonstrates what's actually going on during the process of winding. And my Zoom chat is broken. I can't see the chat. Perfect. All right. But you can see what is going on here. So if you press 1 through 4, that will actually show different camera modes. So if I go 2, that's showing what's actually going on the winder, and the movement is a little sensitive in this mode. Not gonna lie. And then if I press 3, this is showing the actual point where the toe is contacting the mandrel. So this is kind of moves along at the same rate as the toe does. And then if you press 4, this is showing sort of the underside of the case. And then this little display up here is just showing what level the toe is at each point on the case. We're eventually hoping to use this simulator to actually model the entire wind of the case. We're not quite there yet, but it can at least sort of show the behavior of toe a little bit. So I'm going to go ahead and actually demonstrate one of these, what I was talking about in terms of the mandrel. So if I go 4 here, so it's going to start here. And now we are going to do a sideways pass. This is what a TABA looks like. Oops. Switching cameras makes it go a little wonky. Oh well. But anyway, you go across at a given angle, and then you're going to stop. At least this is how the current winder code works. Stopping might not be the most efficient way of doing it, but it works well enough for us. So then we do what we do, the far lock. So this far lock is going to happen. That takes about, it's like usually 2 rotations. So we got about 1 more to go. And I think now we've gone through 1 rotation. So we are going to go ahead and head back. So we're going to move the winder there, try to get the opposite angle that we had.
Jamie, I have a quick question. Do you want someone to field questions in the chat for you?
That sounds great. At least right now when my chat's broken.
Okay, I can do some if other people can just pipe up whenever there's questions.
All right, so now we're going to do the near lock. So that's going to stop, and we're going to run for about 2 rotations. I'll just zoom in on what's actually going on here. And now we're going to go backwards. So our goal is to leave at exactly the same time we're trying to leave with the previous toe. So that's where things get a little bit fancy. I think. Oh, I think it doesn't. Oh, the toe doesn't actually contact this end. That's why. So what we want to be doing is laying a layer of toe down that goes directly parallel to the previous layer. This is what it would kind of look like. Oh, and there's issues from my first thing. But if you really want to make a good case, you want each layer to go directly next to the previous layer. You can try it for yourself. See how close you can get. And now we are right at the end lock. So we're going to go ahead and park it right there. And then we're going to go 2 rotations, then we're going to go back. Anyone have any questions about how this thing's, how the winder is moving, how the toe is being laid down? Now we're going to go directly parallel to that previous one. See how we're kind of starting to form a woven pattern with the previous layers of toe, or previous TABAs of toe? That's what we're going for. And there we go. We're parked. All right. That is enough for this simulator for right now. I'm going to go ahead and go back to my presentation. Any questions at all? I feel like I should be getting some questions here. Now my chat works again.
I think every question was answered that was asked.
All right, cool. Okay, so now we're gonna head to section 2, which is talking about winding theory. So like, why does the toe behave the way it does? I'm sure you guys are wondering, right? Because it's kind of a weird way that it moves. If you park the thing in one place, it moves slowly. If you move it quickly, then the toe moves quickly. Now, the good thing is we can actually model this with some math. So to understand the winding process, we need to understand what happens at the exact point where the toe is being wound on. So we'll try to consider this exact point, the wind point, so as sort of its own like infinitesimal area. So it's like it's only happening in one point. If you've heard the word infinitesimal, you probably know where this is going to go, don't you? So so we got that wind point, and we're assuming that the toe only contacts it at one point. And if we look at that, we can kind of have a look at the angle that the toe is contacting the mandrel. And we can say that based on that angle, when the mandrel moves a specific amount of arc length, the toe will actually move side to side based on that angle, the amount you'd expect it to go. So if the mandrel moves by ds, the toe moves by dx based on this angle, the toe angle. Make point. So yeah, technically these are cylindrical coordinates. The good news is because we're working with calculus, we can pretty much just assume it's a flat plane. And like the ds is infinitesimally small, so it's pretty close to being a linear plane. So we can say that dxt over dsm is tan at. So in other words, so for a given arc length, the amount of side to side we move is given by this angle. So let's plug in a little bit more to that. So using that, so you know that arc length is r theta, right? S equals r theta. Remember that. So we can just do the calculus form of that equation, which is ds equals r d theta. So for a given distance in theta, the arc length is ds. So, and then we know that d theta over dt is omega, angular speed. So we're going to go ahead and we can say that d theta is omega dt. So we can plug that in for d theta, and we can get that ds equals r omega dt. Now we can substitute that back into the previous equation to get that dx over dt. We can, looking at the final result down here, dx over dt is rm omega m tan at. So yeah, to answer Jasper's question, the point of contact is always at the same angle. It's the angle we consider it for this calculus thing for a given in an infinitesimally small step. The point of contact is always at the same angle. However, the point of contact angle goes all over the place as the case is being wound. But for this equation, the angle is constant. So we can say from this equation that the rate at which the wind point moves side to side is determined by the radius of the mandrel, the rotational speed of the mandrel, and the angle between the toe and the mandrel. But what if we want to actually control where it's going instead of just being able to know where it's going? So we can work that equation a little bit further. And because we know that that angle is given by the distance between the carriage and the wind point, you can represent that using d carriage. And if you know how far apart the carriage is from the actual wind point, you can plug that in for tan at, giving you, so the final result here is that so let's suppose, so basically, if you know what the current wind point is and the rate at which you want the wind point to move, and then you know some other constants like the radius, the speed, the distance, then you know where the carriage should be at that point in time. So this equation means that the movement of the wind point from side to side can actually be controlled just by varying the carriage position, as long as you know where the current wind point is. So basically, if you have any arbitrary line shape that's a differentiable function, you can actually control the carriage in such a way that the toe would form that line. Basically, because you just plug in your function for xt prime of t, and you need some way from the actual mechanical system of finding what the current toe point is. Like you probably need some kind of like encoder or something to measure the angle that it's currently winding at. And then based on that, you'd be able to say, if I want to form this line, where do I need to move the carriage? So, however, that currently isn't how RPL winds cases. It's a good thing to know, but it's not actually, currently we don't really have the infrastructure set up to do something like that, because we would need some more advanced sensors, and we need sort of a closed loop system in general. And also, we don't really have any need for that as of right now. So Jasper, let's see. Anna says, what do you mean by current toe point? So current toe point is this green point. It's the point where the toe actually contacts the mandrel. And then Jasper says, can the rotation speed of the mandrel be increased? It's a good question. Well, yes. it's just you plug in whatever the rotation speed is as a constant to these, and then you would be able to figure out how fast things need to move. And I believe if you wanted to, you could probably even express these in terms of d theta instead of dt. So like the x in terms of the mandrel speed. That might actually be more convenient if you're doing like motion equations, like trying to actually build a system with it. You could kind of work it in different ways. Let's see, the difference between xt and xc physically. That's what Diego asked. That's probably easiest to show on the simulator, actually. Where did it go? Oh, there we go. So right now we're looking at the toe point, and you can see as I move the winder, the toe angle increases. So then the toe point moves. XC is actually the point where you click. It's where the carriage currently is. Like I'm moving XC right now, but the toe point isn't moving very much. Make sense? Matthew says, also a good question. Do we actually need some way of controlling the angle with like monitoring the current angle it's winding at, or can you just estimate it? That's actually something I don't know. I've never tried. My gut feeling is that it might be something where you get error that builds up. So like the longer you wind for, the more it gets off from what you expect it to be. So my gut feeling is that you probably need some kind of closed loop system for monitoring the wind angle. However, I don't know that for sure because I've never tried. I've kind of been working on these equations in the simulation for the last couple months. I haven't tested a lot of it on the actual physical winder yet. But I will say it's all 100% like it matches everything we have so far in terms of our winding equations and the physical behavior of everything. Definitely want to do some more interesting testing with this when I get a chance. So the good news, so as I said, we're not currently using these equations for actually winding. So what do we use? Well, thankfully, there's a simpler approximation instead of all this calculus, which is that to keep in mind that if you're winding in a straight line, then you can actually just, if you're winding in a straight line, then the wind point will move at the same rate the carriage does. So a way to think about, does that make sense to everyone? Why, if you're going in a straight line, the wind point moves at the same rate the carriage does?
Can you explain that again?
Basically, if I move the carriage at a fixed speed, the wind point will follow the carriage at a fixed speed. Here, it might be helpful to actually use the Unity editor version, which is because I have a little marker set up where you can see where the wind point currently is. But you also can't really move the carriage from it. See, that little blue dot is the current wind point, or it's above the current wind point. It's where it's currently contacting the mandrel. So if I move the carriage at a constant speed, the wind point follows along with that. If the carriage slows down, the movement of the wind point slows down. If the carriage speeds up, the movement of the wind point speeds up.
And is there like a relationship between those two? Like however fast that one's moving, the other one will move, I don't know, half as fast or something? Because I feel like when you're moving it, yeah. Is it half as fast?
They move at exactly the same speed. So you can say that in sort of a steady state situation, the dx over dt equals dc over dt. In other words, they move the same direction at the same rate. When you just start moving it, there's like kind of extra behavior, but when they're currently moving, they both move at the same rate. So if you just move the carriage along, then the toe will eventually follow it.
Okay, interesting.
Amy, is the XC where the toe is coming out of the carriage?
Exactly. Yeah.
Oh,
I call it the toe start point. I'll go into a little bit how that mechanism actually works, but it's where the toe starts up.
Okay, cool. Makes sense.
So basically, we can say that dxc over dt, because they move at the same rate, we can say that after it's been moving for a while, dxc over dt is tangent angle of, that should be at, not aw. Whoops. Forgot to change that. We can say that the rate that it moves sideways is radius of mandrel, angular speed of mandrel, times tangent of the toe angle. So basically, it moves at a side, so we can move the carriage at a constant speed to get a constant wind pattern. So that way we can avoid using all those complicated equations, but it's also the complicated equations are where this comes from. All right, so moving on, we can now get to a bit of the actual code that generates the TABA. So I kind of went and refactored some of this code. I kind of wanted to give a summary of how this code works in case people have to modify this code. Matt says, what does TABA stand for again? There and back again. So it's one complete process. I put a little guide up if you need it. So first of all, the initial lock. That's really easy. It's just spin the mandrel a few revolutions. That's all you got to do for that. Now, the there pass is a little more complicated. So what this means is, so how do we actually generate the move command for this there pass? Well, the first thing that we do is the X distance. The X distance for the there pass is really easy because that's just the length of the case that we wanted to make, which is a configuration option of the program. It's like length, that's I think wind distance. So, but then how far do we move the X axis? Well, that comes from the toe angle. So the total distance that we need to move the Y axis is just the tangent is 1 over tangent the toe angle. So if we're going at a very high angle, we need to move quite quickly. Or if we're going at so if the toe angle is like 5 degrees, then that means that it's gonna be, the toe is almost vertical on the mandrel. So then we want to go quite far in Y for everything we move in X. So this kind of comes from this equation, though it's not quite the same because we're talking about total distance in terms of instead of speed. But it comes from that equation. And then the next thing that we do is calculate the actual Y distance, which is just from that distance ratio multiplied by the X distance. Make sense? These are little snippets of the actual code that's doing the calculation, or the new version I'm working on. Now the far lock. So the far lock is the step 3. So that's going to be the spinning at this end. So it might think we just need to spin around. Simple, right? Well, not exactly. So there's kind of an extra complexity that you have to think about for this far lock, which is getting the start and end points of the entire TABA to line up. So if you just do a there pass and then immediately turn around, then there's no guarantee that your end point, which I drew in green, would actually end at the same spot where your start point does. Like they just could end at different points. So you might go start here, go around, then go, like stop here, turn around, come back. Well, then you ended up finishing like here, and then that's far away from here where you need to be. So in order to fix that, it takes a little bit of math. So what we actually do is add extra distance to the far lock to ensure that the passes start and stop at the same point. That makes sense. So why do they need to, Daniel says, why do they need to end at the same place? Well, that's a good question. It's basically just because it makes the equations work a lot simpler. And it makes it so you don't have to worry about where the previous pass ended up when you're calculating the next pass. You know, it always ended up at the same exact spot. And I mean, even if you didn't make them end at the same spot, you'd still have to have some way of figuring out where it ended. So you'd still have to do math like this. And I think maybe it has something to do with getting them like correctly opposite each other, but I'm not entirely sure about that. Let's see. So I don't know about that actually. So basically what we do is we want to spin in place, anchor the toe at the end. And we know we're going to do at least a configurable minimum amount of revolutions, but there's also some extra math we have to do to calculate the extra fraction of a revolution. So that turns out to be Y there distance times 2. So we're going to take the total distance we're moving in Y, double that, and then we're going to modulo it by this constant, which basically means how much Y distance is in one revolution. So let's say the total distance we have to move is like 0.75 revolutions for their pass. So then times 2 of that is going to be 1.5 revolutions. So then this is going to increase that up to 2 even revolutions, meaning that the entire thing will take an integer number of revolutions. Sound good? Let's see. Yeah. Matthew says, theoretically, the near lock would be uneven in the amount of toe deposited if the end is not ready to start. You mean the far lock? But yeah, you're right. The end effect locks are definitely going to have different... they're not even at all. It doesn't make any claim that they'd be even. But it's okay because we cut them off before the case is made. So we're talking about the far lock right now, of course. All right, so the back pass is the exact same as their pass. So I don't have a slide for it, but now we're back to the near lock. And this is the equation that took me the longest to figure out what the heck was going on, because I inherited this equation from Carter's wind spreadsheet, and I had no idea what the heck is going on here. So it kind of had to reverse engineer to figure out what it was doing. But I think I did figure it out, and I'll try my best to explain what it's doing. So basically, when the winder lays down two rows of toe right next to each other, we want them to be very close to each other. But each TABA is going to be offset by 1. Like, we want the toe to be next to it. We don't want it to be directly over the previous piece. So we need to move by a little extra amount. So that's called the increment steps. So that's basically, or the increment distance. So that's basically the distance in the y-axis that we need to move to additionally line up with the previous one. And all y-axis distances are expressed in arc length, by the way. So like arc length inches. I wish I'm not happy about the winder being in freedom units, but there's so much installed base. It's currently in inches that I'm not going to change it at this point. So anyway, yeah, so this is all going to, so these are going to be, we want these to line up to next to each other. And the distance that they are apart from each other is actually something we can configure. There's a setting, if you look on Confluence, we have a little settings documented called toe overlap, which basically says these two pieces that are going next to each other, how close do we actually want them to be? So that overlap distance is configurable. So the question is, how far do we need to move the y-axis to get them to actually overlap the amount we want to? And for that, we have to do some trig. So basically, we have this distance between the center lines of the toe things, and we'll call that width of toe times overlap. And then the question is, what is this DI distance here? Like, how far across the surface of the mandrel do we need to move to make this line? So in order to do that, we're just going to set up a little trig thing here. So the cosine of this angle, 9D minus toe angle, is WT times O over D. So then cosine of 90 minus is sine. So then I'm just going to simplify that to get DI equals WTO times over DI. So that is actually the equation that's being implemented here by this line of code. So it's the overlap times the toe width divided by sine of toe angle. So that's going to get us our increment distance. So then that increment distance is going to get added to the normal lock distance. So we're going to move 2 revolutions plus a little extra so that the next layer of toe goes like in sequence with it instead of right on top of it. That makes sense? This is definitely one of the toughest ones to figure out.
What is O again?
O is the overlap. I probably should have made a thing for the variable names.
Is that like a distance, I guess, then?
So that's a percent. So like 100%. So 1 would be no overlap. Okay. 0 would be directly on top of each other. So it's like a multiplier on how far apart we put them. Yeah, Daniel, that's exactly right. So each time you increment it, you eventually get all the way back around. And that's actually how the winder knows to terminate the wind, because the increment distance is once it gets all the way around, that's when to stop. Let's see, Jonathan says, is sine of AT the same as DI? Well, no, DI is a distance. Sine of AT is a ratio. Daniel, oh yeah. Oh yeah, WT is omega T. I don't know. I'm not good with Greek letters. So that's the angular. Oh wait. Oh, sorry. No, it's not. This is the width, not angular speed. This is the width of the toe. Oh, did I mess up the bottom equation? Oh, dang it. I'm sorry. You're totally right. That should be over sine of AT, not over DI. What am I doing? So DI equals WTO over sine of AT. That's what we want. And that's the equation that's being implemented by the code. Sorry, guys. All right. So, any questions on how all this stuff is calculated? All these locks?
Jamie, could you explain how WTO is a percentage again?
So O is the toe overlap, which is a percentage. So toe overlap of 1 means put the toe strands exactly apart and not overlapping each other at all. Like an O of 0.5 would be overlap them by 50%, so move half the width of one toe strand. And then an O of 0 would be directly on top of each other.
So do we want one of overlap? Or
Well,
like,
that's actually something you would configure when you design the case. Like as a general rule, you want the layers to be kind of, the toe fluctuates a little in width. It was a lot worse with our old toe. Actually, the new toe is a bit better controlled, but still sometimes if you want it to like look really clean, you have to overlap them a little bit as sort of a fudge factor. Oh, and also fun fact, I realized there's actually a bit of a mistake in this equation. The old code was using cosine instead of sine here. I think that we never noticed it because we always used about 45 degrees to 55 degrees for the angle. So it actually never really showed up. But that might have been why we had some kind of spooky behavior with higher and lower wind angles, because the overlap was actually set wrong. I think the effect would have been the higher the wind angle was, the more they overlapped each other when they shouldn't have. So that's kind of a fun fact. I think I'm correct in saying it should be sine, but we could try it. And if it's definitely producing bad results, we can, maybe it is supposed to be cosine, but all the geometry says it's sine. Anyway, any other questions? Glad to see all these questions. All right. I think that we can now go to our intermission because I know this was a lot to get through. Can take a break for a few minutes, but I also have a video we can watch to take our mind off things a little bit. Which is, I don't know if you guys know about this. There's a game called Team Fortress 2. You don't have to know anything about the game, but the source code got leaked a few years ago, and then somebody ran a search on the source code for any sort of profanity.
This is the easiest way I could find to refresh the goals when switching maps. To do. This is dumb. This isn't particularly efficient. Too bad. This is a stupid fix, but I don't have time to do a cleaner implementation. This is a bad way to implement Half-Life 1 style sprite fonts, but it will work for now. This seems like a bad idea, but it's fine for now. Move it into place and resize. This is terrible, but VGUI has forced my hand. This doesn't account for children of hierarchy. Too bad. Bizarre vector flip inherited from earlier code. WTF. Multi-threading badness. This will cause a crash later. Grab John S or make John know. This code didn't port easily. WTF does it do? I don't know why. I don't want to know why. I shouldn't have to wonder why. But for whatever reason, this stupid panel isn't laying out correctly unless we do this terribleness.
Use an epsilon, damn it!
This is catastrophically bad. Don't do this. Someone needs to fix this. Yes, this causes a memory leak. Too bad. This is bad dumb code, and more importantly, it's bad dumb code that doesn't make any sense here. My hope is that this code is so offline, never allowed to write UI code again. This shit doesn't work. Why? Has I ever? This is some lame shit right here. This is utterly fucking retarded. And v_hexed binary has no return code. Because nobody could ever possibly attempt to parse bad data. It could never possibly happen.
This is a terrible way of doing this.
You gotta love videos like that.
Are these people describing their own code, or are they shitting on other people's code in the comments as they're like reading through like old
Jack,
code
this
they've
is
been
their
given?
own.
I think those are Valve's
definitely their own
programs.
code.
But I think
I'm just imagining like people having fucking like battles with like they send the code over to someone and then they just get commented like this is fucking trash and then they just leave it in. And
Dude, you've never written some code that's just like absolute garbage, but you know it works well enough.
dude, I don't code. I'm
But like
sorry.
even in MATLAB or something, you know.
It's the,
all of my MATLAB is perfect. I don't know what you're talking about.
It's good when you submit the PR with an apology letter. That's how you gotta go. I promise.
No, I don't need to find a better way to do this other than 15 embedded nested for loops.
It's only
n
O
is
of
to the
n
n.
to the 15th. It's not polynomial, or no, it's not
Nah,
log
O of the n to the
exponential.
n, Jamie.
Yeah. Let's see. All right. So now that everybody's lightened up a little bit, let's get back into some more Winder code. And this is going to be a bit less theoretical. Now I'm going to talk a little bit about the mechanisms of the actual Winder itself. And I've worked on some of these mechanisms. Some of them we have not touched in 3-4 years or more. So this is kind of a best effort thing. And it's not, I'm not going to guarantee that everything here is going to be right. I think Adam's here, who might be able to help us fill in some of the stuff that was around before I started here. But anyway, so what we're going to do in this section is for each major component of the Winder, we're going to talk about what it does in the main Winder system, how it works, its history and why we built it that way, and of course, what's wrong with it and how we could improve it. So I'm going to do my best, and I'm not 100% sure about a lot of this stuff, but here goes nothing. Let's see. So quick overview of all of the components of the Winder. So first of all, we have the toe spool holder. That's up here, and it holds the toe. There's the toe backing roller, which is below the spool holder. There's the toe output, which is behind the mandrel in this. There's the x-axis movement, which is behind the mandrel. There's the bottom pulleys, which are in this area. There's the tape roller, which is over here. There is the y-axis mandrel movement. There's the wind restart system, which is not in CAD. There's the control electronics and the control software, which are not in CAD, of course. A lot of stuff to get through. So also good to keep in mind, Winder CAD is not in a great situation. There is some CAD in existence for this system, but it is nowhere near up to date. Also, I think only me and Neil are the only people added to the GrabCAD assembly who are still at RPL. And only Neil has the permissions to add more people. So we should probably get that CAD. I could send it to people, but should probably fix that. So it's missing some stuff that's added after the initial design, like the current pulley system, the backing roller, the current toe output, etc. And I think there's a lot of dimensions that are subtly wrong as well. So even the size of the 80-20 pieces are not set up right. So I definitely view this CAD as more of an illustration than an actual up-to-date mechanical model of the system. And I definitely think that if we wanted to do serious work on this, we'd probably have to make a new CAD assembly from scratch, or just ban all CAD and take all measurements off the physical object. Those are probably the only two ways to get going. So for stuff that are not in CAD, I'm trying to do hand drawings to the best of my knowledge and the best of my memory. It's better than nothing, at least. So the toe spool holder. This is where the toe starts and where we'll start talking about the Winder. So its function is to hold the big spool of toe up at the top. And what it does is it applies tension force to the toe to make sure the toe is wound tightly around the case. If you have a given thing of toe and you look in the data sheet for it, it'll generally say there's a specific tension that they want you to wind it at, which I believe is generally in the neighborhood of 10 to 20 newtons, if I remember right. So the goal of this is to have a braking setup, which actually provides that tension. So there's metal end caps in each end that go into the spool, and this end cap can be removed by unscrewing it from the 80-20, and then you can put in the new spool, put the end cap back on. And the constant torque brake at this end, it provides some resistance against the turning force of the spool? The turning force of the spool. Jeez, Jamie, what am I doing? What am I doing here? So this brake is kind of cool. What it is it's actually a constant torque device. It has its own special power supply. It's an active device, and it measures how fast it's going and applies resistance in compensation to that. Unfortunately, I don't know what model it is. It says on the thing, but I don't remember, and I wasn't able to find it in any of our purchasing records. But I can't remember the name of the company either. But it just applies a constant torque force. So this toe spool is definitely one of the things. It's one of the things on the winder that really needs to be fixed. I'd say it's maybe the top thing that needs to be fixed, honestly. And the biggest issue with it is that the toe spool is just a press fit onto these end caps. There isn't anything really holding it on there. And what that means is, and the way the end caps attach, you can't really get much pressure going either. You're kind of just setting it between the end caps. You aren't really like actually squeezing it between the wedges. So the effect of that means that the spool starts to slip on the brake once you try to turn the tension over like a pretty smallish value, like, I don't know, 5-10 newtons. So we're barely even winding at like a third of the tension that we're supposed to be winding at, if I remember right. We have tried some kind of band-aid fixes to fix this, like putting rubber between the end cap and the toe spool and trying to like duct tape the toe spool onto the end cap. Those have not really worked well. So because it's under a lot of force for an entire wind. So I think that going forward, the trick is to probably either be to like cut some kind of slot or drill a hole or put a keying feature in the actual toe spool. The hub's made of cardboard, so you can probably drill through it. It also doesn't stick out far past the end of the toe. So I think drilling through it with a drill might not be a good plan, but just because you might nick the toe. But I think that trying to like Dremel a slot or something might be manageable. And or potentially try to make some way of having the sides actually clamp onto the spool is a pretty big issue. So this is definitely something that we need some mechanical engineers who are more mechanical than me to try and have a look at, of making a way of making the system better. All right, now the backing roller. So this is another kind of janky toe spool thing, but it's janky in a different way. So for a little bit of backstory, we were in a tough spot right around the time after Traveler launched in 2019. So what we had to do was we were kind of working with an external company called Stellar Exploration, and they wanted us to make a case for them. And but in order to make that case, we had to make the winder accept a new type of toe. Previously, we'd used toe from a company called TCR Composites. This toe worked fine. It wasn't very expensive, like, I don't know, 50, 100 bucks a roll, which is pretty manageable. And it worked fine. However, when we went to go buy more in early 2019, they told us, like, look, we're really sorry, but we can't sell this to you anymore because at the quantities you buy at, we're actually selling it at a loss to us because of like trying to package and ship such a small load. They're used to selling in much, much, much larger quantities. So they told us that we'd have to do like a minimum order of like $2,000 to $5,000 worth of toe, which is not really what we wanted to do, especially given the shelf life of the stuff, which is, I don't think it's more than a year or two. Right? I don't know. Anyway, it does have limited shelf life. So anyway, we couldn't really get toe from TCR without paying a pretty astronomical amount for it. So that means the winder had to accept a different type of toe. Now, the good news is Elevated Materials, they had some donated toe that was pretty good for us. The downside is it had backing paper on it. So instead of the toe strands just being stuck together on the roll, there's actually a little piece of paper in between each level. So that paper had to be rolled off as the toe was spooled off of the winder. And we needed something to do that, and we needed something to do it fast because we had to wind this case to meet our contract obligations within a couple months. We had to do it over the summer. We couldn't even wait for the next semester. So it was kind of rough. We designed what we could at the time. So what we did was we got a DC motor. I remember this from my days at FRC. There was a motor called the Bag Sim that they sell for FRC teams that let's see. So the Bag Sim motor is basically, it's designed to run and stall for a long period of time. And what that means is it's sort of okay with not actually moving. So how we have it is that motor is held in stall and permanently, and it's just applying tension to the backing paper that's coming off of the toe. So we also have a little voltage regulator on there, just one off Amazon, that's like a current limited adjustable voltage regulator. So we can use that to dial up the voltage going to the motor. I believe it's a 12 volt motor. It's currently running at like 3 volts. So what that means is, so basically what that means is it's only running at a very small percentage of its tension. And so normally running a DC motor in stall would be bad, right? Because DC motors depend on cooling from the like fans inside them. And they also running it in stall means a maximum amount of heat is dissipating to the case. But in this specific case, because it's a motor designed for stall operation, and because it's only running at a small percentage of its power, we get away with holding it in stall forever. And then we just made a little roller with PVC pipe glued to 3D printed end caps that are attaching to these, and then pick the tape. They pick the backing off from the toe as it's being pulled off. Let's see. So it's janky, but it works. We literally made it from like duct tape and spare boards that were sitting around lab. The mounting for the roller, it's kind of just on there, and it's not really catted, and it's made of scrap wood and duct tape, and it doesn't really have a proper bearing. I ordered the parts for fix this, and then they didn't show up, so it never actually got that fixed. And also, there's a bit of an issue with the connection between the motor shaft and the roller. So I don't know what's the best way to actually attach to a bag sim shaft. It's currently a press fit, it tends to come loose at times, if I remember right. Unless we fixed it already. Maybe we fixed it somehow. I don't really remember. But it was an issue in the past. So I think probably setting up some kind of set screw thing would be a little bit better. However, I will say this thing has actually worked properly for a while. So it's actually not something I'm really worried about, but it is something to know it exists. And probably making a proper mount for it would be nice to have at some point. All right, now we are going to talk about the bottom pulleys. So what's going to happen is the job of these pulleys is to reorient the toe from the downward direction coming off of the toe spool to the actual toe output point. This is sort of a 3D view, or my best attempt at one. This is an actual side view. So there's one big pulley here that handles, because the toe moves back and forth along the spool, so you need a big pulley here to kind of handle that as far as it can move back and forth. And then that's going onto a pulley that goes sideways, and then it goes through these guys going across, and then out the toe output point. Now, I will say the original winder design actually had an S-beam load cell on this middle pulley, the goal being to try to actually measure the toe tension. Now, they ended up taking that off for some reason. I don't exactly know why. Adam, do you know? I was wondering. Is Adam here?
I don't think Adam is even here.
Oh, never mind. They're here, I guess not. Okay, never mind. So, guess it'll remain a mystery for a little longer unless someone knows. But it's definitely something to think about. But I think that they ended up removing that load cell because probably because either they didn't need it to control the tension, or they weren't getting any useful information out of it. Because the good news is the current constant torque brake kind of solves that problem in and of itself just by being a constant torque brake. So it kind of does the sensing all by itself. All right. So now we're going to talk about the toe output. So the goal of the toe output is to be the point where the toe actually comes out of the carriage and starts going onto the mandrel. So this toe output thing can be a little tough to get right. So basically what you'd want is something that will allow the toe to come off at a variety of different angles, and then also but then also not have a lot of frictional force on it. So basically how we used to do it is we had these two types of rollers. So we actually grabbed these from like an air compressor hose, and basically the toe would pull against the rollers and it could move out in either side, and it could switch between them as it wanted to. However, when we switched to that new wider toe 2 summers ago, it started getting jammed up in the bottom here, like right in these little cracks. So it like got folded over on itself and snagged and broke. So we had to ditch that. And currently we're just using a plastic eye bolt that's embedded in a block of wood. Now, this is nice because there's no way for the toe to get caught or frayed. However, I think that if I remember right, it has pretty high friction, and it just sounds creepy when it's going because it tends to like vibrate back and forth. It always seems like either it or the toe is about to break. But it has worked for several winds, so we probably don't have to worry too much about it at this point. Ideally, we could get something that would combine both of these in a way like that would basically provide like a bearing, but then also that like basically something that would allow it to go at any angle, but also didn't have a lot of friction. I have seen some winders that kind of like try to move around, and then but they try to like dynamically adjust the angle of a flat bearing. That was something I saw, but I don't know about that. It seems kind of complicated to add a whole new motor just for that. I still think it's possible to do a better mechanical only solution. It's good to think about. This is kind of my rough idea of like what we want. Something like a bunch of small bearings in a circle with no gaps between them. I believe that I saw some kind of something that looked like this. Oh. Maybe we could try something like this. Basically, this is like on a bearing. Yeah, so then there's a shaft that goes across, and then the toe comes out of here. I don't know like what it would really look like. Sorry for my horrible mouse drawing. So this, I think that I saw Dare using something like this in one of their videos for their winder. So it could be something to think about. But coming up with a better toe output would be really nice, is I guess what I'm saying. All right, now let's get into the actual CNC parts of this. So the x-axis movement is what lets the carriage move back and forth. And it did an interesting way of designing it. Basically, they have a stepper motor with a gear on the shaft of it that then meshes with a rack gear that's attached to the 80/20 track. So the carriage can slide back and forth, the gear meshes with the rack gear and moves back and forth. This system works. It's probably fine for what we need it to be, but it's also not perfect. From what I've heard, it seems like a gear drive like this is probably not the best choice for a long motion axis like this, because it has a fair amount of backlash. Like, I don't think the tolerance is much better than like, I don't know, 50 mils, 100 mils, which is okay for a winder, but it's not perfect. And also, let's see, another issue is that the rack gears are actually smaller rack gears that are welded together. So even though the welding was like done fine, there's a little bit of a discontinuity where they touch. So there's always like a little bump. And also there's I know that in the past there's been some issues getting the motor to actually mesh with the gear down the entire way. Carter said he had a lot of trouble getting it adjusted, but thankfully that's not been an issue for a couple of years. For that, so we haven't really had to mess with it. And then I feel like if you were doing it over again, it'd probably be better to use like a lead screw or a belt for that. I think long lead screws are kind of expensive. I don't know if they're more expensive than this. I don't know. I think belts are generally what I've used for like 3D printers and such, but I don't know if a belt really go this long. Luca,
long lead screws are remarkably expensive.
What are you guys using for the
Belt's
CNC?
probably the way to go.
Yeah, I think that's what you probably want to use.
Yeah, we're doing big belts.
Anna's question, is our winder custom made? Absolutely, yeah, it is. This was entirely built by people in RPL.
Oh.
That's why it's so janky.
Okay.
But also it's cool.
That makes a lot of sense.
So it actually went through a lot of evolutions. I'll talk about that a little more in the control system section, but we've had it since like, I don't know, 2012, 2011, 2013. Also, fun fact, the person who originally designed it was Jordan Noon, who was CEO of Relativity until recently. So it's like his first it was like one of his big projects at RPL.
RPL's baby, I guess.
Let's see. So, oh yeah, the other issue with the x-axis movement is that there is no cable guide. The cables just fall onto the floor. So that has caused problems in the past when the cables get caught on things and bring the entire wind to a screeching halt because the cable is caught on a drawer or something. We mostly fixed this about a year or two ago by wrapping up all the cables into a big bundled cable, which on the downside, it makes them about 5,000 times harder if you want to change one of the cables. But on the upside, it means that they are a lot less likely to get caught, and they're a bit better protected from like rubbing on the floor. One of them almost had the insulation run all the way through. Anyway, so now let's talk about the tape roller. So the job of this tape roller is to dispense what's called compression tape for wrapping up the case. So this is part of our case wind process. To be totally honest, I'm not 100% sure why we need it, but basically how it works is you do a layer, you wrap the layer in plastic compression tape, then you put breather on top, then you vacuum bag the entire thing, then you pull vacuum on it, and then that basically squishes down all the toe from the previous layer to make sure it's pressed as tightly as it can possibly go against the layer before. Then you take the vacuum bag off, take the breather off, take the tape off, and then you can wind the next layer. And of course, it's always the RPL sport to see how long you can get carrying the end of the tape. We've managed to go all the way from RPL lab to Tommy Trojan, which is like, I don't know, getting close to like a quarter mile, maybe an eighth of a mile. Yeah. So we can get pretty far with that thing when we're unwinding the winder. So this tape, so the tape roller is pretty, does anyone know why we actually need to wrap it in compression tape instead of just putting, oh, Julia says the tape helps stop the breather from sticking to the carbon. That's perfect. Okay. So that's why we need the compression tape. And this
What's
mechanics.
a breather again?
Breather is basically, it's like wool material. You put it, it's hard to explain without better presentation, but basically it's something that goes between the vacuum bag and the stuff under the vacuum bag, and it helps make sure that the vacuum bag, there aren't like pockets of air. Let's see. So so how this tape roller works is pretty simple. There's just a bolt that acts as the spindle for the tape. And then there's metal blocks on the front right here that you can screw it down to adjust the tension. And then the roller itself can be moved to either side of the mandrel, because it's not if it were only on one side of the mandrel, you wouldn't be able to access the entire distance. So when winding the entire length of the mandrel, you actually have to stop in the middle, move the tape roller over to the other side, bolt it down, then keep going. It's a little annoying. But thankfully the tape is pretty forgiving to do, so it's not a huge deal. Let's see. So, what's going to happen after that? So, the tape roller does also, of course, like everything on the winder, have its fair share of problems. The tensioner on it doesn't actually work that great, like this thing. So we usually have to have someone hold the tape to add a little extra tension to it. And if you try to tension it too far down, it is pretty prone to snapping the tape. There's definitely kind of a trick to getting it working. So, and also putting on the tape with this requires at minimum 2 people, one to hold the tape and tension it, and one to stop the winder when it's getting close to the end of the thing so it doesn't crash. Yes, that's a very lame sentence to have to say. Our current CNC stuff is not very smart. We're working on making it smarter, I promise. So it's not smart enough to stop at the end, so you have to manually stop it. But it does work. All right, so now the Y-axis movement. This is also, I don't have this in CAD, but I do have CAD for the pulleys, which I actually 3D printed these pulleys because to try to do a bit better than the system that was on there. And they're still a little bit of a mess, but they work. So the Y-axis movement's job is to rotate the mandrel. So that might sound easy, but this mandrel can take quite a lot of force to rotate. It needs quite a lot of torque at easily, like, I don't know, 5 to 10 rotations per minute. So not going super fast, but it does need a lot of torque because you have like a 4-inch radius thing and you're fighting like 20 newtons of force on it. I don't know the exact unit conversion, but that turns out to be a lot of torque. So we have an absolutely humongous NEMA 34 stepper motor. It's one of the largest sizes available powering that mandrel. It might be a little bigger than we need, but better to have bigger than smaller. And we also have a belt that provides a 6-to-1 gear ratio with that mandrel. And then the mandrel itself is mounted on 2 chucks that are welded to metal axles. So that way we can loosen the chuck to remove the mandrel. I think they're like lathe chucks, but so they grip the mandrel from the inside. You can switch them out with like a 6-inch or whatnot. So the Y-axis movement has been through a couple of revisions. It actually used to be chain drive. And as anyone from FRC knows, chain is a pain. So it's not exactly known for having low backlash. And in addition, we had a lot of issues getting it tensioned. As it turned out, this was actually because the screws that were holding the motor in place were like bottoming out, so they weren't tightening all the way down. So the motor was like moving as you wound, which I completely missed this. Dennis caught it. If he hadn't caught that, we would have been having this problem still with the tensioning. But the chain movement had some issues and a lot of backlash. And also the stepper motor was actually missing steps that time because it didn't really have enough torque. Like even a huge stepper motor like that, trying to drive something this huge at a 2-to-1 gear ratio was kind of overwhelming its torque limit. But what I realized was we had a lot more, the motor could run a lot faster. So we replaced it with a 6-to-1 pulley system. So less backlash, much more gear ratio. This was about the biggest pulley we could possibly fit on there. And the 3D printed pulleys are a little bit jank, but they've also worked consistently for years. And I don't think that we'd be able to buy pulleys in that specific of a size, like 208 tooth and I don't know, 208 divided by 6 teeth for these specific shaft sizes. So I actually used an open SCAD script that generates the pulleys based on the sizes that you need. It's really cool. And they're huge, so 3D printed parts are better when they're big, like they have more strength. And it's worked fine for what we need. All right, any questions on any of the winder mechanicals of this? I know it's a lot, and I know basically all of them I said this is janky because yada yada. So, but that's just how it be sometimes. Any questions at all? I'm sure there's stuff you want to know about this thing. Even if your question is, why?
Why did we make one instead of buying it?
So yeah, that's a good question. So there are some currently, there are some commercially available winders. I believe that the most common one you hear about is the X winder. With this one, so that the X winder is not nearly as large as this. I believe it maxes out at like 4 or 6 inch cases and nowhere near this long is basically the short version. That's, I think, the main reason. I don't know if there's other reasons. Probably it's also a little bit to RPL's a spirit of building stuff ourselves. Oh, wait, James, you have experience with the X winder? Ooh, do tell.
I have experience with it crashing after I try and execute G-code, but I jog the axes and it works fine. So troubleshooting that currently is top priority, but TLDR, it sucks.
Huh. Let me know if you're still getting stuck with it. I might be able to take a look or something. If it takes G-code, then it should be hackable, I guess.
Yeah, we'll have a conversation about that. I'm looking forward to that.
All right. So Jonathan says, can you go over again what the tape roller is doing? What the case when the case is being winded? Does anyone happen to have a? Let's see. Here we go. Picture of the current toe that we use, or have any? I really want to pull up a picture of it. I don't know the model number. I'll just search for carbon toe in general, see if I can find one that looks like what we have. All right. Well, okay, no dice, so I guess I'll have to do a crappy mouse drawing, but that's kind of our only option here. So when the toe comes out of the roller, it's one piece that has a backing piece and a toe piece. So the roller would the roll would be like there, and there's a thing of toe coming downward from it. And then the goal of this backing roller is to take off the backing from that and wrap it around this roller as the toe is being wound. Make sense?
Jamie, could you explain how the 3D printed gears are mounted again?
The 3D printed gears. Okay, that was something that Neil helped out with a lot. We were both working on it back before he had bigger and better things to do. So the 3D printed gears, the small gear actually is keyed and fits into the keying slot on the stepper motor shaft, and the this one is actually attached to some like random go-kart part that Neil found online. That's it's a set screw and fits on a 1-inch axle. So it's bolted through to another hub that then set screwed to the shaft. The shaft is really soft, which I know from experience based on trying to use some other set screw setups that basically just scratched it to high heaven without actually being able to transfer enough force. I 3D printed one of these that had like 6 set screws that were all like M3 size. It did not work. Like cracked the plastic trying to get them tight enough.
So are those like 2 gears in contact with each other? Is what you're
No,
saying?
they have a GT2 belt going between them.
Oh, okay, I see.
I wish I had a picture of it, but I don't think I do. Keep an eye on it. I'm sure we'll get some pictures someday. All right. Any other questions about mechanical stuff? Nope. All right. All right. Time to get this show back on the road. So, winder electronics and software. So the first thing that I'm talking about with the electronics is the wind restart system. And this is like my project as a freshman. So this is something I worked on a lot. And basically it has one job alone, which is to provide an absolute position reference for both of the axes. So what that means is before that, basically just said wherever the winder boots up, that's the 0 point on both axes. But the wind restart system means that you actually have some way of saying, okay, this point here on the axis, that's like 30 inches from the start point. And it sounds simple, but previously we didn't have anything like that. And I'm serious, they used to actually like make a Sharpie mark to mark where they started the wind and then try to like set it back to there. And it was just covered in Sharpie marks at the end. It was very jank. I hope Carter's not in this call. Let's see. What we've got here is so basically how this works is it uses a Hall effect sensor. And this Hall effect sensor senses a magnet that is attached to the x-axis. So the magnet is attached to the carriage. And then there's a little Hall effect sensor mounted to the 80-20. And then on the y-axis, the magnet's just stuck to the steel chuck. It's just attached on there. And then the magnet's mounted to the metal thing that holds the chuck. So it senses as that magnet goes past. So these Hall effect sensors are super cool. They sense the presence of a magnetic field. They're pretty simple to work with. And then the second half of the wind restart system is when the code knows that when it starts a wind, it homes to those end stops. And then you can say, hey, skip the first 47 tabas, and it'll just add the increment step size 47 times. And then it'll be starting the 48th taba. That's why I've made such a big deal about increment step, because it's basically the math that powers this restart system. Because before we had this restart system, you actually couldn't restart a wind layer partway through. If anything happened to the wind layer, including like running out of tow or like the power going off or like somebody pressing a key that stopped the motors, you had to actually completely unwind the layer and restart it from scratch. With the restart system, we don't have to do that. We can start in the middle. So, So if any part of the winder fails during wind, you have to manually unwrap. And now you can. This means that you can restart layers from a specific TABA number. If you look at the command line wind.py, it has documentation for like how to tell it what number to start at. So I will say the system, the weakest link with it has been the Hall effect sensors mechanically, because almost every wind, like clockwork, at least one of them gets either bent over, damaged, or just destroyed, and then we have to solder on a new one. So they're very vulnerable. I even tried putting them in potting compound, doesn't seem to work. I think what happens is like when people take off the vacuum bag, it kind of gets bunched up at the end and can like bend them over and break the wires. And so they're kind of vulnerable. So we definitely need a better housing for these Hall effect sensors. It'd be much appreciated. But I will say, keep in mind, they need to be pretty close to the magnet to activate, like 2-3 millimeters at absolute most. So they're fairly sensitive. Also, the current way that the Hall effect is mounted on the x-axis actually blocks the carriage from accessing like the back 2 inches of the mandrel. It's kind of in the way. So if we could come up with a different mount for that, like screwed to the desk instead, we could reclaim about 2 inches of winding space. That's something to think about. Let's see. So now let's talk about the electronics. My voice is starting to die. We'll see if I can keep it on life support. So the fundamental job of these electronics is to power the stepper motors. And what they do is they let you move these motors by a precise distance. They're accurate to 1/2000th of a revolution. So how it works is you have Gecko Drive GM215 controllers, and they regulate the power to the motors, and they also execute motion commands. We'll go over what that means in a bit. So then we also have a custom circuit that I almost wrote that in all caps just out of habit. The custom circuit that converts Hall effect signals to motor controller switch inputs. So basically, we have the signals coming from the Hall effect sensors, and then it converts those to sensor, something that these motor controllers can input. And finally, we have a 60-volt power supply that powers the motors and a 5-volt wall wart supply that powers the restart system, the Hall effects. So, electrical schematics. So we have so I drew up these schematics from memory a couple months ago. I'm not 100% sure they're right, but I'm pretty sure because I've manually rewired this once or twice. So I just kind of want to put these on here for reference if anyone wants to see them. So you got PSU, wall wart, Hall effect end stops, GM215 motor controllers, and the big steppers. All right, so the power supply has is one of the main parts of the system, and it needs to supply quite a lot of power. Based on some calculations from the Gecko Drive site, we can say that these motors are probably using about 5 amps of power, 5.3 amps at their current settings. So we have this big TDK Lambda 60-volt 10-amp power supply. But it turns out that this power supply is not exactly the best power supply for this job. So in the past, we've had 2 of these power supplies blow themselves up in the last 5 years or so. I was there personally for one of them. I took it apart. There's just some little surface mount component on the bottom that just blew itself to bits. We've also had one set of motor controllers that were also just suddenly dead one day, which was a big deal. And so at the time, we thought it might be due to stray pieces of tow getting into the winder because it is conductive. So it makes little conductive particles that are in the air. And they can be a little bit dangerous to electronics. So we actually put all the electronics in a like ventilated housing. And we have not had a power supply die since then, but we have had 2 motor controllers die since then, both of them at the same time. And honestly, that one's still a little bit of a mystery. It could have been a lightning strike. Could have been somebody came at them with an axe, but a really microscopic one. Our current best theory is that it has to do with a power supply issue. So if you read the data sheet and information for those motor controllers, it talks about how when they've stopped the motors, they dump a bunch of power back into the power supply and like charge it up. And they basically specifically say, do not use the exact type of power supply that we are using because they don't handle that very well. And these power supplies are designed to provide like a very consistent voltage, which these motor controllers don't need actually. They're okay with like a rough and rowdy power supply. But they're not good with something that's trying to regulate the power supply. So these motor controllers and this power supply are not really supposed to be used together. And our theory is that that's why the motor controllers are killed themselves. But we're not 100% sure. And we're currently in the process of switching to a new power supply, Automation Technologies, which is actually the correct type of power supply to use with this setup. It's unregulated, just a transformer and some capacitors. Let's see, Diego says, are these schematics on Altium? These schematics are not in Altium because then I'd have to make Altium parts for all this stuff. I just wanted to draw them up for reference. If someone wants to put them in Altium, that would be cool. But
I was just wondering, like, what is the values of the resistors that you have written?
Oh, I did that because I didn't remember what value they are, but they're probably like 1 to 10K. I don't think it really matters. It's just a pull up.
Oh, okay, I see.
So the motor controllers. So currently we have these GM215 motor controllers, and they're responsible for all of the motion control operations. Basically, they have their own software and programming language that is in fact Turing complete, by the way. And we basically just tell them, move the X and Y axes to these coordinates, and they do it. But these motor controllers, first of all, they're not made anymore. So if they die again, we won't be able to replace them. We cannot buy them. And the reason for that is that they are a royal pain to work with. The code is not well documented at all. I was never even able to figure out what units velocity was set in. I finally had to time it and find that one of their velocity units was 3.8 of a revolution per second or something. So if you set the velocity to 1, it takes 3.8 seconds to go around. It's very weird. It's not 4, it was 3.8. And they're also they're not well documented. They have major software glitches, and they're just a royal pain to work with in general. So we're currently in the process of switching to a new Arduino-based system. So basically, we can keep using our existing motor controllers, but switch them into dumb mode, which is basically where they just act as a stepper driver, and they take pulses from something else and then use those pulses to control the motors. So instead of it being the motor controllers control themselves, we have something else controlling the motor controllers. And the upshot of that is we can actually just replace them with regular motor controllers if and when they die. without having to like rewire, do everything with the code and the electronics. And the Arduino also provides some other benefits, like basically like having more persistent like homing and remembering what the current position is, and better like speed and feed rate system. I've been looking into it over the last couple of days, and it looks pretty promising. We can definitely get it to work and work a bit better. That's like what I said about fixing that issue where it goes too far. We can make it automatically stop itself, which is going to be cool. Let's see. So what have we got here? So as far as the control software, this is our last component that we're going to be talking about. I'm sure you guys are psyched. So the control software's job is to basically tell all the stepper motors where to go in order to create a layer of the motor case. And it also provides a user interface for stopping and starting the wind. So basically saying like, okay, start winding, and then pausing it, stopping it, restarting it, and also running other functions like the tape wrap. So the control software uses all of the equations that we already discussed and for part one. And then they take a config file, the format of which is documented on Confluence. What the heck, I might as well pull it up. Let's see. If you look up Winder config files on Confluence, I have like a bit of a diagram of what these parameters are and how they're configured. It's mostly just the stuff we've talked about today. But so you configure all that stuff, and then it turns that, using the equations we talked about in part one, into a complete case program. So the control software has gone through a couple of major revisions. So it was originally written in like 2012, 2013. It was actually in LabVIEW, and they used like National Instruments DAC stuff to generate the step pulses for the motors. And back then, the Winder didn't even, it was not even really like as smart as it is now. It basically just did the dense layers only. So it kind of just moved in one direction, and it wasn't even really a CNC at all. They just used it as part of a much larger winding process. Then in like 2013 with Traveler 2, as you might have heard about in the history presentation, Carter and some other people figured out how to actually make the winder replace almost all of the carbon winding that was done on the case, removing pretty much all of the manual carbon winding. That's when it started to get a little smarter, and we started to get some more sophisticated equations and procedures going. So in 2016 or so, they replaced all of the LabVIEW stuff with the GM215s. I'm not entirely sure when that happened. I think it was sometime between 2013 and 2016. And fun fact, so this code actually worked using a spreadsheet. This is what I inherited when I started at RPL. Just here's this spreadsheet, go make it into a program. So this spreadsheet had like the initial version of a lot of these calculations. There's a few bugs in there. They're mostly right. And you put all the information from from your case into that spreadsheet. That would then output a bunch of step numbers. You copy paste the step numbers into a text file, which was the program. Then you use the Gecko motion software to send that text file to the motor controllers, and that's one layer. And then you just have to keep hitting send over and over again. Or maybe you could make it loop. I think you could make it loop. Never mind. But it was a very manual process. So in 2018, we made the current version, which is custom Python scripts on top of the Gecko motion software. So we actually reverse engineered and sort of modified that driver to let another application in Python control it instead of just having a graphical interface instead. That took a while to figure out how the heck it worked. It's a real mess. But now it paid off, because now we're able to have a script that automatically runs that software. And we can automatically generate the motion control program. Same kind of general idea as the program the previous system used, but generated automatically. And we have wrapper scripts, command line wind.py, tape wrap.py, that automatically run that kind of stuff. All right. So the current software is better than what we had, but it still has some issues. So we were having some issues in the last year or so with some intermittent communication dropouts that pretty much were just stopped talking to the motor controllers until they were restarted. And we're currently thinking that was due to power supply issues. I turned on a lot of debug logging, and from the logging that I saw, it looked like the motor controllers just got suddenly restarted for no reason. Then they like wake up and like, hey, I don't know what the heck I'm supposed to be doing. Dude, are we supposed to be moving right now? I don't even know. That was kind of the stuff I saw in the debug logs. So I suspect a power supply issue. So that's why we're going to try replacing the power supply as the next thing. If that doesn't fix it, then we'll probably just have to wait till we replace the GM215s, because I'm not entirely sure what else could be going on. The communication protocol with those things is very janky. This would only make sense to programmers, but basically it relies on getting accurate timings out of thread.sleep on a desktop, like to the millisecond. Like if it takes too many milliseconds to respond, the entire communication just sort of dies. So that's really bad programming practice. It can't even express how bad that is. It's pretty messed up. Other issues are that the command line interface is not really interactive. There's no way to like hit pause. You just have to either stop it or let it keep going. It'd probably be cool to make some kind of user interface. With the current setup, there's not much you can really do anyway. The G-code based and Arduino based setup will have more options. It looks like you might actually be able to set up like a physical button that's like feed hold. So pause the winder without actually canceling what it's doing, which would be pretty dang neat. Another issue, sometimes it doesn't respond to Control-C. Normally, if you're trying to stop the program, you hit Control-C. Sometimes it doesn't actually respond because the way Python handles Control-C is stupid. It just generates an exception, which you could catch and then never respond to. If Control-C doesn't work, hit Control-Z, and that'll like force stop it. And then another issue is that the program has no way of knowing when the tow runs out. So it has to be manually stopped and restarted, which is kind of a pain when it's about to run out of tow. All right, let's see some questions in chat. Is it possible to get Zoom on the Winder computer so that we can use remote control to let people type commands for the Winder? Actually, I could do one better, which is you can actually run it over SSH. So you can log in with a remote shell and then drive the computer that way. Though granted, that doesn't really work if it's on USC Wi-Fi. It only works if it's at a private house because USC doesn't do port forwarding. But it's definitely possible to remote control the Winder. And if people really wanted, you could probably make the current software like networked so you could control it remotely. It's definitely doable. Any other questions about electronics or software? I know for all you mechies, there's probably a lot of weird stuff that you aren't entirely sure what's going on, but it's important to think about from a software perspective. Let's see. For tow running out, can't use a 3D printer filament end switch. So that's actually a good question. So you could probably use a switch to detect when the actual tow filament stops. But the problem is by that time it's too late, because when you actually have to stop at the end of the layer, and then you can really only like do a clean switch of the tow when it's about to do the first lock. So you'd have to know at least one TABA before it runs out of tow. But I actually do have a thing to talk about that, which I'll get to in a second. I was thinking about that a while ago. Any other questions? Nope. All right. Let's see. So now this is kind of my soapbox area where I just wanted to talk about some ideas I had for how the current Winder could be improved a little bit. And to be honest, it had always been my plan to kind of try to do this stuff in my senior year. And it certainly looks like that isn't going to happen now. So I guess I just kind of wanted to put these ideas out there. And if anyone wants to try to do them going forward, this is kind of the research that I've done so far. So this is a plan I've always called the next gen Winder, as it had fixed some of the real issues with the current Winder. So one of the basic ideas would be to replace the constant force brake that we have with what's called a clear path closed loop motor. So I happened to hear about these a while ago. What these are, they're really, really cool. They're like a special type of stepper motor that includes an automatic controller. And they have some videos about it. They're crazy cool. One of the things you can do is set them to constant torque mode. So it has like a force sensor in the motor shaft, and then it will try to do something until the force sensor is sensing a specific force. But it's also like smart enough to detect if it's like spinning freely, it will stop. And you can actually adjust it by sending signals in the power connectors here. Or not power connectors, just connectors. But you can actually control the force dynamically. So if we were to replace this brake, which is kind of dumb, with this clear path motor, first of all, it would let us adjust the tension dynamically. And second of all, it would mean that the current brake, it doesn't pick up slack. It's only a brake. It's not actually a motor. So sometimes what happens is as you're winding, the toe will go slack, like because suddenly it was stuck and then it comes loose. So then it goes slack. And this brake can't actually pick up that slack. This motor can't. It can actually spin backwards in addition to just being a braking force. So it'd be a much more functional tensioner. So yeah, so it acts as a source of constant continuous torque. That one is adjustable from 0 to 2 Newton meters, which is what I calculated as what we'd need. I don't have the actual like work I did, but I'm pretty sure that's the amount we need. It actually pick up slack, and also it let us actually hit the winding tension that's specified for the toe instead of just taking a total shot in the dark by like adjusting the brake randomly. So first issue is that it require new mountings and a new shaft coupler, and if we want it to actually work properly, a new like toe spool holder too, so that it could actually grip the toe and apply all that force. Another issue is that the relationship between torque and force, as anyone knows from physics, depends on how much toe is actually left on the spool. It's like the paper towel roll problem. The more you take off, the smaller the radius gets. I think I measured it. It decreases by about 50% between full and empty. So it's definitely not an effect you can ignore. So that leads us to big idea number 2, which is actually add a sensor to detect how much toe is left. I found this thing, the VL6180X time of flight distance sensor. And what it does is it senses the distance that this roll is away from 5 meters to 100 meters. So we could actually mount it next to the roll and it would detect how far away it is and therefore how much toe is left on the roll. So this would kind of lay the groundwork for automatically adjusting the amount of tension as the toe unwinds. So this setup would require some kind of brains to tie it together. So my recommendation would be to try to make either this could be a custom circuit board, or we could just build it from dev boards. You could probably build this around an Arduino, or you could build it around an mbed microcontroller, or kind of whatever someone has experience with. And you add in a time of flight sensor, a knob to adjust the torque, or the force, not torque, a display to show the remaining toe and tension, a USB connection to a computer. That way you could actually connect it to the desktop and it could report how much toe is left, giving the ability for it to automatically stop itself. And also the 5-volt PWM output to the ClearPath motor. I think this would be a pretty cool project to try going forward, and it'd really take our winder to the next level, really. It'd solve a lot of problems. It solved the problem of no way to know when it runs out of toe, solve the problem of doesn't pick up slack, and solve the problem of the tension not being right in one go. I will say, when I was working on this, I could never get people to sign off on the funding for this. Back when I wanted to do it, it would have been about $1,000. Now it's more like $500 because we already got a new power supply and other stuff. And as I said, I always wanted to do it this year, but I'm probably not going to be able to. So I'm really kind of leaving it up to you guys to decide if you want to try this and how to do it. And that's all I've got for today.